Take a look at a few more examples of using u-substitution. So this function here, the integral of sine squared of 3x cosine of 3x dx. Now, trying to build the intuition of what do you want to pick for your u, to do u-substitution, some strategies will be things underneath square roots. That's an option. Things that are raised to a power. It's another option, or maybe even things on the denominator, or things in the exponent. There's a few common ones that we'll often be picking. Now here, you might be thinking, well, what if I chose 3x, right? We looked at the integral of cosine of 2x. What if I picked the inside of the parentheses there? Could that work? That could, but then what you're looking at is you're trying to integrate sine squared of u cosine u. That doesn't really help with the problem that we have. The problem that we have is that we have sine squared and cosine, and I don't know how I could possibly pick something like that. So if we rewrite this, this is sine of 3x quantity squared, cosine of 3x dx. Now, when you write it like this might instead give you a little bit more insight. What if I pick the thing inside this parenthesis? What if I pick sine of 3x? Would that work? The strategy of knowing when that choice works will often be found when you find the dx. Does that derivative part allow me to substitute everything I need to? So let's see an example. Let's see this. So if I choose let u equal sine of 3x, then when I take my derivative, do differentials, I take the derivative of sine of 3x. We have to use chain rule. Derivative of sine is cosine. I rewrite my inside, and then I multiply by the derivative of the inside, which is 3. And then I throw on the dx as well, because I took the differentials. Now, notice, again, we said we can move constants around. That's cool. The issue is when there's variables. That is the problem. We can't divide by the variables. So we're trying to figure out, does cosine of 3x times dx, does that appear up here? If it does, we did a good u-substitution. And indeed, we do have cosine x 3x, cosine 3x dx. So I divide this by 3. Now I can substitute things in. This becomes the integral of u squared, because sine of 3x, that's my u, so that's squared, times this du over 3. But I know, again, that I can pull out this constant of 1/3, and I'm left with du. So I have u squared du. Integrate this by adding 1 to the power and dividing by the power. So I have a 1/3 u to the third divided by 3 plus a constant. So I have my u, we said, was sine of 3x. So I have sine cubed of 3x divided by 9 plus c. So there we go. That is our final answer. Again, check yourself if you'd like. Do the derivative, and you will get that. Let's take a look at another example here. So here, often the strategy of picking things inside parentheses, picking things in the denominator are good choices. So if we pick this denominator here, not the square part, but just the inside of the parentheses, let's see if that choice works. So if I say let u equal 1 minus 2x squared, then the derivative of this is going to be negative 4x dx. This is magical, right? I don't even have to move this constant over. I have a negative 4x dx. All that appears there. So that's marvelous. So my substitution now consists of simply putting on du on the top divided by u squared. Now this one just requires us to rewrite u squared as the different exponent. This is the same as the integral of u to the negative 2 du. So now I add 1 to the power, and I divide by the power, and then I have plus c. But I substitute in for x, so I get a 1 minus 2x squared to the negative first over negative 1 plus c, And we can simplify this if we want to. This would be negative 1 divided by 1 minus 2x squared plus c. And so that would be my solution. That is the antiderivative of negative 4x over 1 minus 2x squared, all of that quantity squared dx. So these are, again, some examples. We'll look at a few more because there's a few more tricks that we would like to see before we really are able to go out there and attack any type of integral using substitution.